There is a 46,000-ton concrete structure hanging in midair. This isn't a static building, but an entire bridge being slowly rotated on a pivot the size of a dining table. Below it, one of the busiest railway lines remains in full operation at full speed, carrying thousands of lives, unaware that a giant is moving right above their heads. If the calculations are off by even a fraction, or if the turning mechanism jams halfway, we aren't just talking about billions of dollars in losses, we're talking about a total infrastructure catastrophe. In recent years, the internet has been flooded with videos of a giant yellow machine named the SLJ-900, often nicknamed the Iron Monster. That machine went viral because it could assemble bridges like stacking Lego blocks. But for engineers in the field, that machine is actually considered technology of the past. Today's challenges have changed. We are no longer just connecting roads on flat land. We are talking about piercing through typhoons in the open sea, drilling through fragile karst mountains, and rotating massive structures in the middle of dense cities without stopping the economic heartbeat. Let's start on land. The classic problem in infrastructure is how to build a new bridge that must cross existing train tracks or highways without closing the lanes below. Shutting down a major railway line like the Beijing-Guangzhou route for months to install scaffolding is a logistical nightmare that is impossible to accept. Conventional solutions had hit a dead end. Thus, the swivel construction method was born. The concept sounds simple, but the execution requires serious guts. The bridge is built parallel to the train tracks on an empty plot of land beside it. Once the main structure is fully poured and hardened, the entire bridge is then rotated horizontally, like the hand of a clock, to reach its final position and connect with the pillar on the other side. In Hebei province, the Baoding Bridge broke the world record for this technique. Engineers had to rotate a 46,000-ton structure across a 52.4-degree angle. The time they had? Only 68 minutes. Let that number sink in. A load as heavy as a battleship had to shift with precision in little more than an hour. The key to this industrial ballet lies in a component called the spherical hinge. This is a giant bearing that supports the entire weight of the bridge. For a load of 46,000 tons, the hinge diameter reaches 6.5 meters. This is where both the magic and the greatest risk lie. This hinge consists of a concave bottom cup and a convex top cup made of high-grade steel and ultra-high performance concrete. The manufacturing precision is absolutely absurd. The curvature error of the spherical surface must be less than 0.5 millimeters. This is equivalent to polishing a giant contact lens, but this one must withstand thousands of tons without cracking. To ensure the bridge rotates smoothly, friction must be minimized. With a special PTFE or Teflon-based lubricant, the static friction coefficient is suppressed to below 0.1. This means a structure that heavy can be moved with relatively little force. If this friction fails to be managed, the bridge could stop rotating halfway over the tracks, hanging without support, becoming a permanent monument to failure. But rotating a bridge is just one chapter of this story. The next challenge is speed and extreme terrain. We return to the beam launcher machine. The old machine, the SLJ-900, had a fatal flaw. It struggled when it had to pass through narrow tunnels. Often, the machine had to be partially disassembled just to get through, then reassembled at the end of the tunnel. This wasted time. Furthermore, concrete beams for modern high-speed trains are now made longer, reaching 40 meters, and heavier, breaking the 1,000-ton mark, to reduce the number of joints so trains can run more stably at speeds of 350 kilometers per hour. The old machine wasn't strong enough to lift this load. This is the reason for the birth of Kun Lun. Developed by the China Railway Construction Corporation, Kun Lun isn't just an upgrade, it's a total redesign. Its lifting capacity rose to 1,000 tons, but its deadliest feature is adaptability. Kun Lun is designed like a giant centipede with dimensions that fit perfectly within the profile of high-speed rail tunnels. It can slide through mountains carrying a concrete beam inside its belly without needing to be disassembled. As soon as it exits the dark tunnel mouth, it can immediately install a bridge on the edge of a cliff. This machine is also equipped with laser sensors and advanced rubber tires that work in sync. This is vital because Kun Lun is often assigned to cross-sea projects like the Fuzhou-Xiamen high-speed railway, which is prone to typhoons. When working over the sea, strong winds can topple a machine this tall. Kun Lun has a system that automatically adjusts the machine's posture to fight the wind, designed to keep working in level 7 winds and survive without destruction in level 17 typhoons. This is a transition from simply building connections to conquering the most ferocious elements of nature. Speaking of conquering nature, nothing is more ambitious than the Shenzhen-Zhongshan Link project. This is the spiritual successor to the Hong Kong-Zhuhai-Macau Bridge, but with the difficulty level dialed up. This isn't just a bridge, it's an infrastructure cluster combining a suspension bridge, artificial islands, and the widest underwater tunnel in the world. Let's break it down one by one, starting with the artificial islands. To transition from a bridge to a tunnel in the middle of the sea, they needed land. The old way of dumping rock and sand takes years and damages the marine ecosystem. Here, engineers used the percussion steel cylinder method. Imagine a giant steel cookie cutter, 28 meters in diameter, 40 meters high. 57 of these cylinders were driven directly into the seabed using the world's largest vibratory hammer. The visuals are brutal but effective. Once the cylinders are embedded to form a perimeter ring, the water inside is pumped out, then filled with sand. The result is a stable, dry island in the middle of the sea in a matter of months, not years. This method also minimizes the spread of mud, a crucial compromise to protect the habitat of the Chinese white dolphin in the highly sensitive Pearl River estuary. Once the island was done, the real challenge began: the Immersed tube tunnel. This is the world's first underwater tunnel to feature 8 traffic lanes. Water pressure at a depth of 40 meters is deadly. Ordinary concrete risks cracking. The solution is steel-concrete-steel structure. The tunnel walls consist of steel plates on the outside and inside, with self-compacting concrete filled in between. However, there is a huge risk here. The toughest challenge is pouring concrete into that closed steel cavity without leaving a single air bubble or void. If there's an air pocket, deep sea pressure could crush the steel plate like a soda can. To prevent this, an intelligent casting system with thousands of sensors was developed to guarantee 100% concrete density. The most critical moment in this project occurred during the connection of the final tube, coded E23. Because the tunnel was built from 2 opposite directions, the final gap between these tubes had to be closed with millimeter precision under the darkness of the water. They used a folding joint technique. A hydraulic mechanism pushes a connecting segment out like an accordion to close the gap, then locks it permanently. Failure at this stage means a catastrophic leak that could flood the entire tunnel. Above sea level, the bridge portion of this project is no less terrifying. The bridge deck sits 91 meters above sea level, equivalent to a 30-story building, providing space for the world's largest container ships to pass underneath. Because it's in a typhoon zone, this bridge uses a steel box girder cross-section design that has been tested in wind tunnels to withstand wind speeds of up to 88 meters per second. Without this aerodynamic design, flutter vibrations caused by the wind could twist and destroy the suspension bridge. Now we leave the sea and head to the mountains of Guizhou. This province is a nightmare for highway contractors. 92.5% of its territory is mountains and karst rock. Building a flat road here is impossible. The only two choices: bore a tunnel or build a bridge from one peak to another. This is where the Beipanjiang Bridge, or Doog Bridge, stands. This bridge holds the record as the highest in the world. The vertical distance from the bridge deck to the river surface below reaches 565 meters. If you dropped a rock from up there, it would take a long time before you heard the splash. The valley below is too deep to erect support scaffolding, so this bridge was built using the balanced cantilever method. Segment by segment is built jutting out from both sides of the cliffs, held by steel cables, hovering over the abyss. The biggest risk is the meeting in the middle. Both sides of the bridge must meet with an error tolerance of only a few millimeters. There is one interesting fact about precision at this altitude. The final connection process, or closure, usually has to be done at night or in the early morning. Why? Because the heat of the sun during the day can expand the bridge's metal. A slight change in temperature can alter the length of the steel and cause the two sides not to fit when they are about to be locked. Engineers have to fight not only gravity, but also temperature. Not far from there is the Pingtang Bridge. Its main tower is 332 meters high, making it the tallest reinforced concrete bridge tower in the world, taller than the Eiffel Tower. Its design is slender, resembling a diamond or a local dancer, aiming to reduce wind load. To build a tower this high efficiently, they used the hydraulic climbing formwork technique. The concrete mold climbs up automatically using hydraulic jacks. This allows construction to run 24 hours a day non-stop. The big question is, what is all this for? Why spend trillions and take technical risks this huge? The answer lies in the impact felt by the humans around it. Regions like Guizhou and Yunnan were once isolated. Local farmers often let their harvests rot because the cost and time to ship to the city were too expensive. Bridges like Pingtang cut travel time between valleys from 50 minutes via dangerous winding mountain roads to just 2 minutes crossing the bridge. Agricultural logistics changed completely. Fresh products can reach the market in a matter of hours, increasing farmers' incomes by up to 600% in some areas. More than that, China has begun transforming this infrastructure into tourist destinations. At the end of the Pingtang Bridge, a sky bridge service area was built, complete with cliff hotels and museums. People come from far and wide just to see this engineering marvel. Its location was even deliberately integrated with the world's largest radio telescope, FAST, creating a new science tourism route.